Yeah, so good morning. Welcome back. So before I start with the technical stuff, actually, got a lot of feedback that I should write bigger. I'm trying to do that, but please help me out. Like I'll forget about it again. Please just, let me know when that happens, and I'll try to do my best. I also wanted to use better chalk, but actually I cannot find it right now. So yeah, no, okay. I guess someone was responsible for bringing better chalk. As soon as you show up, please give me the chalk. Is it better than this? At the very least, oh yeah, great. Okay, perfect. Excellent, thanks. That's extremely convenient. You just carry that around all the time? Okay, third. Okay, guess I forgot about third. Anyways, please remind me when I'm writing too small. So the goal of today's lecture is not to talk about 3-sum anymore, but we'll move on to the next family of problems. And basically, the high-level ideas of like the first part is that we'll try and find a graph or matrix problem which behaves similarly complicated like 3-sum. And maybe the first problem on matrices you could think about is matrix multiplication. So I figured I'll spend some time and write down something about matrix multiplication so that we can very quickly talk about this. And then we'll actually get to like the fine-grained problems that I want to talk about in detail. Okay, so matrix multiplication really is this, you've all seen it. Nevertheless, let me go through the definition once, right? The input consists of two matrices, A and B. The task is to compute their product matrix, A times B, which is defined by this equation, right? The ij entry in the product matrix is defined as like the inner product of the kth row in the first matrix and the kth column. Sorry, the ith row in the first matrix and the jth column in the second matrix. So this expression, basically. So I always, in my head, I always take the column and map it there, right, and you take the inner product, which is obviously easy for matrix multiplication, but let's try to keep the move in mind because later we're going to do it also for different operations other than the normal matrix multiplication. Okay. Now, maybe you've heard that there is this super advanced line of research which actually studies faster algorithms for matrix multiplication than the trivial one. The trivial algorithm is basically you can evaluate this matrix product in time n cubed because you have to enumerate all indices I, j, and k. For all of these, there are n choices, so you can compute matrix products in n cubed time. But there is this extremely clever algorithm from like already 1969, I think, due to Strassen, who showed that you can express this 2x2 matrix product. This is just the product of two matrices of size 2x2. Using this very complicated expression, like, as all entries are not determined not as like a single entry, but as a sum of several, specifically of these 7 numbers here, all of which can be computed using just one multiplication. So the non-trivial thing which is happening here is Strassen observed that you can multiply 2x2 matrices, not with 8 multiplications, which would be like the naive upper bound, but in fact with 7 multiplications. And then the second part of the algorithm is that you can bootstrap this observation actually to multiply not only 2x2 matrices, but n by n matrices, very big matrices now, with a significant speedup. So in particular, the running time you obtain is n to the log base 2 of 7, which turns out to be n to the 2.81. In any case, it's truly subcubic. Okay, so matrix multiplication does admit very non-trivial algorithms, and this also led to the longer line of research. To state it properly, typically people write the exponent of matrix multiplication. We will give it a name. The name is omega. So omega is the smallest exponent, such that matrix multiplication can be solved in time n to the omega. Maybe this helps. And using this notation, which is actually very standard and which you'll probably see also in a bunch of research papers, then this can be summarized as, omega is at most 3. This is like the trivial upper bound on the matrix multiplication complexity, just the naive algorithm. Strassen's algorithm can be expressed as omega is at most 2.81. And then there has been a lot of work on this, like really dozens of papers. The state of the art is just from this year, which proves that omega is at most 2.3716 and some more digit behind there, which is actually important. And making a lot of progress on these digits. Okay. So what's the bottom line here? From the viewpoint of fine-grained complexity, matrix multiplication is often considered an easy problem. It might even happen, and some experts claim that if you give it some more time, eventually we'll have the upper bound omega is equal to 2. So it's very well possible that in 100 years, actually, matrix multiplication runs in best possible time. Recall, obviously, n squared is the best you could hope for because already your input, say the matrix A and B, consists of n squared entries. So if you could prove omega equals to 2, you could basically say, even though it sounds a little bit weird, that matrix multiplication is in linear time. Right? So that's basically how we'll view matrix multiplication often. We'll just pretend for now, well, they're not done with this yet, but maybe at some point they will be. Then matrix multiplication truly becomes an easy problem. Okay? So this is not the problem we were looking for. This is not a hard problem on matrices or graphs. So what we'll do next is basically we'll try to find another problem, which maybe is hard. Okay? And actually, I'm going to offer you 3 different problems, all of which could be candidates. And the cool thing about them is that they look very different. Oh yeah, the chalk is much better. First one is triangle detection. And this, the input is an undirected tripartite graph. Can you read this? All good? Cool. Let me throughout denote the vertex parts by x, y, and z, and some edges. So, the graph basically looks like this. You have x, y, and z. There's some nodes here, and there's some edges here, but there's no edges inside these parts. And the question is, is there a triangle in the graph? Now, triangles have already been in the Excel sheet yesterday, right? So a triangle is just, or if you've seen them all in lecture, is there 3 vertices which are connected by all edges? First problem. Let me give you the problems first before I actually talk about them. You can already form an opinion about these. The second one is Boolean matrix multiplication. So here the input is 2 matrices. So this is a problem of matrices. But this time they do not necessarily contain integers, but they contain bits, 0, 1. And the task is to compute their product, but not exactly their integer product, but their Boolean product. So I'm now going to find another matrix product following a very similar style. Let me denote it by this. Whatever, you can take any symbol, it doesn't really matter. It's also a 0, 1 matrix of size n by n. And it's defined like this. ijth entry of, the product is the OR of A, I, K and B, K, J. Okay, so if you compare that to the normal definition of matrix multiplication, we have replaced the sum by like a bitwise OR. And we have replaced the product by a bitwise AND. Let me give you a quick example. So if I compute the Boolean product of these 2 matrices where, say, here you have a row with 0, 1, 1, and here you have a column with 1, 1, 1, 0. Then in the normal matrix product, the inner product of these vectors is 2, right? So I would put in the appropriate entry, I would put a 2. But this is a Boolean product. So actually, I took the OR of 0 and 1, that's 0. 1 and 1, that's 1. So already I'm going to be 1. 1. Okay? Another way to view this is you just take the normal matrix product, but then you replace all numbers in the output matrix By 0 if they were 0, or by 1 if they were positive. Right? Good. And there's a third problem, which is transitive closure. In this case, we're given also a graph, but it's directed. And the output is that you test for every pair of nodes whether there is a directed path from the first to the second. Okay? You might have heard the term transitive closure because sometimes this is the graph which is basically obtained by adding all shortcuts, following the directed edges in the original graph. Just a very quick example, right? Directed graph maybe looks like this. Now if I tell you these vertices u and v, right, the output should be yes, or like the output is an n squared, like you return actually n squared different many values, right, for every pair of nodes. But for this particular pair of nodes, the answer will be yes, because obviously nope, not that one. You can't trace that path. Are these problem definitions clear? OK. Then, well, I'd say that they look very different, right? On the one hand, we have a problem on directed graphs, triangle-like. The next one is a matrix problem, no graphs at all. And the third one really requires directed graphs, otherwise it's pretty trivial. It does not look like triangles or something like at all. What's your guess? What's the relation between these problems? Maybe even further, do you think these are hard problems, as in they actually require, say, cubic time, that would be like the trivial running time for triangle detection, or do you think you can solve them faster? Does anyone want to offer an opinion? Yes?
Can be called the same as matrix multiplication, because they can be solved by matrix multiplication.
Good. So at the very least, Boolean matrix multiplication should be solvable by matrix multiplication. Because exactly what I said before, right? Obviously, you can just compute the normal matrix product and then replace the positive entries by 1. So this problem obviously should be in time, n to the omega. Oops. Yes?
Triangle detection with matrix multiplication, because if you take the adjacency matrix and you square it, then wouldn't you get? You would at least know that two vertices have some sort of.
Cool. Yes. Absolutely correct. Matrix multiplication basically allows you just to compute the two paths in the graph. Or actually, for every pair of nodes, it allows you to compute how many two paths you connect these two nodes. Keep that observation in mind, by the way, with the squaring the adjacency matrix. That's going to be helpful. Yes?
Could you also do a similar thing for transitive closure, where you take the matrix, which represents the adjacency matrix, and take it to the nth power to see all paths between things above n or something like that?
Very good.
But then you can use repeated squaring.
Repeated squaring. Excellent. OK. Wow. Very good. So yeah, it turns out all of these problems are in time n to the omega. Maybe up to some log factors, but let me ignore them. Good. So these still do not really look like hard problems. They still probably will turn out to be easy problems, as in if omega is 2, they have optimal algorithms in time n squared. But let me just very quickly show you at least that there's some non-trivial relation also between these. It's actually very easy to see because in the end you always said, well, you can use matrix multiplication to solve them, right? But it turns out these problems are really also special cases of each other. As in triangle detection is a special case of Boolean matrix multiplication, which is a special case of transitive closure. And it's very easy to see. I'm just going to give you a picture. So detecting if there is a triangle in a graph is exactly as someone said. Basically, you take the adjacency matrices of view this. OK, Okay, let me draw something. If I delete the edges in here from the graph, like the x to z edges, I view the edges here as a matrix A. This is a matrix B. Then the Boolean product of these two matrices determines exactly for which of these points there exists a two-path. Okay? The normal matrix product would even count this, but the Boolean matrix product really just determines is there a two-path. So that really is a special case of Boolean matrix multiplication, which it does not only test this basically. Like triangle detection only tests is there a single triangle in the graph. Boolean matrix multiplication does the same thing just for all edges. Right? Still, you have like matrices A and B. You can view it as like you have all edges present here, from x to z, and it determines for every edge is this in a triangle. Okay, so the output is now much bigger. It determines for n squared many objects, for n squared pairs, are they in a triangle. In particular, you can test whether there's at least one triangle because you can just test if there at least a single one in the output. Okay, and now I claim this is also a special case of transitive closure because, or maybe use this notation, reduces to this, reduces to that. Well, because you can just take this graph. Whenever you had an edge before, just direct it in this direction. Now the same for these, which you direct in this direction. Right? And if you now compute the transitive closure in this graph, it's going to report exactly all the shortcuts from x to y, which is all the two paths in the graph. Okay, so also it's a special case of transitive closure in the case where you have basically a tripartite graph, or three-layered graph. Okay, so all of these problems are in time n to the omega. All of these problems even have some sort of hierarchy among them. So maybe we should consider slightly more complicated problems after all. And the idea is that let's consider next the weighted variance of these problems. Okay, so all of these problems, as we will see, admit a very natural weighted variant. After that, we're going to check again whether they're easy. I guess I'm going to erase this part. Good question. I'm going to ask you the same question after the end of the lecture.
Okay.
So, okay, let me give you 3 new problems. Next one is called negative triangle detection. Okay, so the idea is the same. You're still given basically an undirected graph. Tripartite graph with no parts x, y, and z. And now you also have a weight function, which takes edges to integers. And again, I'm just going to write integers, but it's the same assumption as yesterday and is always basically in finite complexity. This is just polynomially bounded integers, right? You cannot write extremely large numbers here. The output is there a negative triangle? So is there a triangle x, y, z such that, well, the weight of the edge xy plus the weight of the edge yz plus the weight of the edge zx is negative? Okay? You need an example? Maybe, this is a negative triangle. Right? The edges add up to whatever, which is negative. Next problem. Let's try to make Boolean matrix multiplication have weights. Now, of course, you could think of integers again, but that's actually not the variant I'd like to go to. Instead, let's consider problem which is called min plus matrix multiplication. Okay, so for this problem, again, you're given two matrices. And the output is a third special matrix product. It's the one, let me write it like this, star B, which is defined as follows. The AI entry, the IJ entry in this matrix product is now, maybe you can already guess it, the minimum of all k AIK plus BKJ. Okay, so again, we take matrix, like normal matrix multiplication as up there, and we replace the operators by something different. This time we replace sum with minimum and product with plus. So maybe at this point, like it's already the third example. In fact, you can define a very general family of matrix multiplication problems for various addition and multiplication operators. In like math terms, you would say for every semi-ring, you can define a matrix product. These are different semi-rings which we use, and we study the complexity of the matrix products. Actually, maybe a very quick example. Which one did I have here? So if you have a matrix which has a row with 1, 4, 3, and 7, you have a column with 5, 2, 2, and 3. Right, and their min plus inner product would be the minimum of all numbers 1 plus 5, which is 6, 4 plus 2, which is 6, 3 plus 2, which is 5, and 7 plus 3, which is 10. So it would be 5. Okay? Good. Finally, well, if you consider the transitive closure problem again, right, the task was basically determined for every pair of nodes, is there a path from the first to the second? Now with weights, it's just natural to ask for the shortest path. So you want to determine for all pairs of nodes, what's the shortest path from one node to the other? And this is, this extremely famous all pairs, shortest paths, or APSP. And again, let me write it formally. The analogy of this is still you're given a directed graph, right? Oops. And it has edge weights. It's reasonable to ask for proper integers here, but actually, I like to think about the problem in terms of non-negative integers because then distances make more sense. Turns out they're equivalent, so I'm just going to work with non-negative integers for distances. The output is to compute the distance, which is the length of the shortest path from U to V for all pairs U and V. Are we on the same page with what distance means? Right? Take the shortest path in terms of the weight function. Take the length of that. Yes?
Why is the non-negative case the same as the negatives?
Yeah, it's a good question. I guess I'll leave it as an exercise. It's not particularly easy to answer at this point. OK. Good. So for instance, Let me try to reproduce the same graph as already failed. Who cares? And if you add some edges here, right? What is the shortest path? Oh, that's just one. That's convenient. Right, so to go from U to V, the shortest path would be, no, I again took the wrong one. 7 plus 10 plus 2 plus 7, which is what? Which is 1426, maybe? OK. OK. So this is the next family of problems. Again, you can solve them in cubic time, which is very obvious for a negative triangle, right? You just enumerate all pairs of nodes, check whether they're not only a triangle, but a negative triangle. You can solve min plus matrix multiplication in n-cube time, because again, you just have to enumerate all pairs of indices I, j, and k. Actually, if you think about this matrix product for general semi-rings, the same is true for every semi-ring. You can always compute it in n-cube time. Just apparently, sometimes you can do it faster for the normal one. And for the third problem, actually, maybe you haven't necessarily seen it, but there is this famous Floyd-Warshall algorithm, which solves APSP in n-cube time, basically. So yeah, what's your guess? Can we do better this time for any of these?
So you could use min plus matrix multiplication with this repeated squaring to get APSP.
Oh, that's already very good. Fair. We'll see that in the next part. Yes?
Negative triangle is, of course, like min plus matrix multiplication.
Sure. OK, so going, OK, I'll get back to that in a bit. Any other remark? Yes?
Does Strasson's algorithm not work for every?
Perfect. That's exactly what I wanted you to ask. Exactly. We have Strasson's algorithm, right? So Strasson's algorithm, it looks like a good approach to solving something like min plus matrix multiplication. But turns out, what does Strasson's algorithm rely on? If I didn't go to into it in a lot of detail, but they have this very clever way of not expressing the matrix product as like the standard way, but using a bunch of cancellations like here, right? Out of a sudden, you have minuses in there, and also in these equations, sometimes you need minuses. So stuff is going to be strategically added together such that it cancels out in the end. And now try to mimic the same behavior with min plus matrix multiplication. What you would need is something which cancels the minimum operation. So you need the minimum base kind of to be invertible, which is simply not true. Right? So Strasson's algorithm, or the techniques behind Strasson's algorithm, they really work, mathematically speaking, for rings, for invertible plus operations, basically. They will fail very miserably, though, for proper semi-rings. So indeed, we don't have any algebraic tools available to solve min plus matrix multiplication faster than the trivial bound. Like a small caveat about that is actually as an exercise in the extra sheet. Yes?
You said we need something to cancel that minimum.
Yes.
Why maximum doesn't do that?
Well, because you say you have three numbers, right? Let's say I want to write something like 7 plus 2 minus 2. It's just 7, right? The 2 is canceled. Well, if you take the minimum of 7 and 2, which is 2, and then you take the maximum of 2 and minus 2 or 2, whatever, then you get 2 and not 7. It doesn't it's not really what we want an operation, like an irreversible operation to be. OK. So let me give you a couple of more remarks, and then we'll have a short break. So yeah, it turns out people have thought a lot about maybe not necessarily the first two problems, but definitely the third problem to get faster algorithms there. And well, it turns out also that there has been a lot of progress. There has been a lot of algorithms, but all of which had very minor improvements. So a list of APSP algorithms. Let me at least write one or two running times. So APSP algorithms. So the first one, obviously n cubed. which is not trivial because you still have to argue that n cubed actually is an n cubed time, right? Is due to Floyd and Warshall independently, though, in 62. And then people have started to shave lower order factors, right? Now, Amir said we don't care about logs, and we won't. But let me just, just to demonstrate how hard it is. So the first was something maybe like a log to the 1/3 shave by an important paper due to Fredman, 75. And then there really has been a lot of points in this list until the end. There was an algorithm in time n cubed divided by 2 to the omega of root log n. This is a running time, like this is the saving, which is, it's better than any polylog. So this is a better shaving than, right, maybe to avoid confusion. This is shaving more than, they say, a log to the 100. But it is not quite a polynomial improvement. So this running time is not of the form n to the 3 minus epsilon. And over the time, people started believing maybe this is best possible. So what they really came up with is the APSP hypothesis. Which states that there is no APSP algorithm in time n to the 3 minus epsilon for all epsilon bigger than 0.
Can you write a little bit bigger no, just
This one? Sure.
this and the one above it.
Sorry?
This and the one above it as well.
Okay.
Thank you.
Yeah, they're not so important. Don't worry about them too much. But I should have put the reference here. This is due to Williams. Somewhat recently, I think 2014. That big enough?
Yeah. Thanks.
Good. So the APSP hypothesis really states there is no APSP algorithm that runs in truly subcubic time n to the 3 minus epsilon. And as it turns out, this really is is a great source of hardness, which led to a bunch of lower bounds. And well, I didn't write these problems for no reason. Like the fun part about this lecture is that we'll see actually that these two problems are also cubic time hard, assuming the APSP conjecture. Right, which is surprising because Alpers-Schroeder's path is like this really complicated problem. You have distances in graphs, whatnot, and a negative triangle looks pretty easy in a sense, right? Because you just have to find a triangle which in total has negative weight. But as we'll see, this is in fact APSP hard. And as many of you have already observed, maybe these problems also follow like the same order. Like negative triangle is also easier than the others. So in fact, we will prove that these problems, negative triangle, min plus matrix multiplication, and APSP are subcubically equivalent. But OK, let's take maybe 5 to 10 minute break now. Maybe let's say 10 minutes. See you at 9:50.